Hello, my name is Ahmed, and along with my project partners Stephen, Robert, and Aditi, this is our project, which is on automotive stock price prediction. In recent months, there has been global discussions about certain trade policies, tariffs, and political decisions made in the US. One sector that comes to mind that can be very much affected by these policies is the automotive industry, especially with the increasing public engagement from Tesla CEO Elon Musk. Our project is inspired by these recent economic and political discussions, and we want to analyze stock trends in response to factors like public policy, global events, and influence. We have selected four different car companies to represent diverse automotive sectors. These include the American market, Ford, European market, Volkswagen, Asian market, Toyota, and electric grid market represented by Tesla. The goal of this project is to identify influential factors and forecast future stock prices across these four key market segments. Now we want to give a little background on our data sources and how we acquired our data. Our historical stock data was sourced from investing.com. This is a reputable and up-to-date market data provider. The chosen companies, as mentioned previously, are selected for their global relevance and their sector diversity. Ford, Volkswagen, Toyota are the leaders in their demographic markets, and Tesla is the overall leader in electric vehicles. Data was accessed through the general history data, which is a section of the investing.com website for each company. The stock price data was manually downloaded into CSV formats for streamlined processing. Each member picked a specific car company, and we downloaded individual CSVs for each car company. The data cleaning and pre-processing process involved us standardizing dates formats to align stock timelines across all four companies. We chose a data range of 2020 to 2025 to encapsulate all recent political decisions as well as previous economic factors that and global factors that may have also been in effect for these stock prices. We removed all missing values and unnecessary columns to ensure data cleanliness. We renamed certain headers for consistency across all datasets, and we synchronized timeframes for accurate cross-company comparisons and forecasting. Ultimately, our goal is to produce individual stock forecasts for each company, as well as group-level insights into how traditional and electric vehicle segments may behave in the near future. Now I will let my group mates discuss more about the project in detail.
I'll be walking you through the key goals of our project. First, our main objective is to apply time series forecasting techniques such as ARIMA, LSTM, Facebook Prophet to accurately predict stock prices of major automobile companies. Next, we aim to analyze regional stock performance. For this, we selected Tesla, Toyota, Ford, and Volkswagen to represent electric, Asian, American, and European sectors, respectively. This helps us capture both company specific and regional market behaviors. We also plan to incorporate external factors like Google Trends data and major political or economic events such as elections or tariffs that may influence the stock trends. Another goal is to generate both individual company forecasts and the group level insights so we can draw comparisons between categories like electric versus traditional or American versus Asian automakers. An important component in is understanding the influence of leadership. For example, we want to explore how figures like Elon Musk impact stock volatility through public statements or decisions. We also aim to build interactive visualizations to clearly present our forecasts and finding in a user friendly format. Lastly, we want to conduct a comparative market analysis to uncover global investment opportunities and determine what factors drive performance in different regions. These goals together help us bridge predictive modeling with real world stock behavior and market context. Thank you.
Hello, everyone. I'm Steven, and I'll be walking through the technical implementation steps our group is taking in DSCI 592. The first step is using the clean historical stock price data we prepared in DSCI 591. This includes four companies: Tesla, Toyota, Ford, and Volkswagen. Since the data is already cleaned and aligned by date, we can now focus entirely on model development. Step 2 is implementing our forecasting models. We'll be using ARIMA, a classical time series model, Profit, which is good for automatically handling seasonality and trend shifts, XGBoost, a machine learning model that learns from engineered features, and LSTM, a deep learning model designed for time series data. Next, we'll evaluate each model using 2 metrics: mean absolute percentage error, which tells us how far off we are on average in percentage terms, root mean squared error, which shows how large our prediction errors are in absolute terms, with greater emphasis on larger mistakes. Let me break this process down a bit more. Step 1 is straightforward. We're using the clean stock data from DSCI 591, so no additional acquisition or pre-processing is needed. In step 2, model implementation, each of the 4 models serves a distinct purpose. ARIMA is helpful for capturing linear trends and autocorrelation. Profit is flexible and well suited for time series with clear seasonality or abrupt changes. XGBoost will help us learn relationships based on features like lagged prices or rolling averages. And LSTM will allow us to model long-term dependencies in the sequential data. Step 3 is model evaluation. As mentioned, we're using mean absolute percentage error and a root mean squared error to measure accuracy. We'll apply time-based cross-validation training on a segment of the timeline and testing on future data. This simulates a real-world forecasting scenario and gives us a better sense of generalization. In step 4, we begin tuning the models. For ARIMA, we'll try different combinations of P, D, and Q parameters. Profit allows us to adjust change point sensitivity and seasonal components. XGBoost will be optimized using grid search, and for LSTM, we'll experiment with the number of layers, learning rates, and use early stopping to prevent overfitting. Step 5 focuses on interpretation. XGBoost will give us feature importance scores, helping us understand what influences the predictions. Profit provides trend and seasonal decomposition, which makes the forecast more transparent. LSTM interpretation is more complex, but we'll analyze how well it tracks directional changes and key trend reversals. Finally, step 6 is dashboard development. Ideally, we'd like to present our forecasts and model evaluations through a visual dashboard, potentially using tools like Tableau, Streamlit, or Power BI. This could include elements like company selection, forecast versus actual, price plots, and performance summaries such as mean absolute percentage error and root mean squared error. However, depending on time and technical feasibility, we may not fully implement a dashboard, but we will aim to present our results in a clear visual format regardless, even if it's through static charts or a simplified interface. And by following these steps, our team will be able to develop well-evaluated and interpretable forecasting models. Whether through a full dashboard or clear static visualizations, we aim to present our results in a way that is both informative and accessible.
There are several metrics we can look at in order to evaluate our models. Mean absolute error is the average of absolute errors. Root mean squared error is the average magnitude of the error, which penalizes larger errors more. Mean absolute percentage error is the average of percentage errors, which is good for relative error but can be unstable if true values are near zero. Finally, the coefficient of determination, or R squared, shows how much of the variation of the target variable the model explains. For price movement direction, we can also consider accuracy, precision or / recall, and the F1 score, which is a balance between precision and recall equal to 2 times precision plus recall divided by precision times recall. For a time series such as this, we can also use walk-forward validation, which involves training the data on T0 to Tn, and then validating on Tn plus 1, then continually sliding the window forward and continually training the data, thus preventing leakage from future data. Each of our models, after evaluation, have different ways of improving them. ARIMA, one major way of improving it, is via differencing, which involves subtracting the previous value from the current value which helps keep the station's series stationary. Profit can be improved by looking at seasonality. Seasonality is when data shows repeating cycles over fixed intervals. For stock prices, that can include for stock data that can include things like a greater volume of stocks being traded on Mondays after the market reopens. Seasonality tuning can work by adding custom holidays or events or changing or in order to show or evaluating weekly intervals, thus showing how the data is affected. XGBoost. For XGBoost, feature engineering is very important. This can include things like lagging features or rolling mean, such as or other data points, such as 14-day volatility, and looking at technical indicators such as MACD or RSI. Finally, for LSTM, we can scale the data using things like min-max scaler or standard scaler. Finally, all of these can improve by reframing the problem. While we're looking at stock prices, we can also improve models by looking at by trying to predict other data points, such as price direction using classification methods, volatility using regression methods, and other similar data related to stock, which can help improve the model by showing how it applies to other parts of the data.